After a brief hiatus, we're back. Today we're going to go over making functions. I'm going to start a new GitHub repository for this. I will call it USGS data and functions. And using USGS data to explore how to write your own functions. So in class so far, we've spent a lot of time using functions. So other people have written these functions that we've been using in class. And today what we're going to do is write our own functions. And this is really useful when you have a task that you're repeating over and over and you don't want to write out the full code over and over. You just need to write out the sort of bare minimum code to do the same task. That'll become a little more clear as we do this. So I'm going to go ahead and clone or download this. I'll open an RStudio instance. It's probably going to have some random code up. Oh, it doesn't. I'm going to do version control git. Let's go CSU. Huh. Okay. We'll create the project. Okay, so we just started with an empty project like we have for the last few classes. So we'll do file, new file, R markdown. USGS data and functions. I'm just making our typical new R markdown document. I'm sure there's a way to control this so it doesn't generate all that text I don't need. Just saving the name. Okay. And now we need to load some of our key libraries. So we'll start with tidyverse as we always do. Then we're going to load one called data retrieval, which we've used once in class before, but today we'll focus a little bit more on its core functionality. And then we'll do another one called DY graphs. This is just a really nice interactive way to plot time series. And I think that should be it. I might load some other ones as we go. So the first thing we want to do is download USGS data using data retrieval. So data retrieval is this package written by the USGS, and it's meant to access both USGS data and the water quality portal. Today we're going to focus on data from the USGS. So we'll go ahead and get data from the Poudre River. And I forget NWIS. So we're going to use the read NWIS daily value function, and I'm just using the question mark to sort of remind myself how the syntax works, and I'm going to go down to the sort of examples here. So what it takes is a start date, an end date, and some site codes. Let's go back to the internet and figure out what this site code is for USGS on the Poudre River. It's this number, which we'll find a place to copy it from. Great. So we'll just focus on the Poudre River since that's where we all live, or if you live in Fort Collins. So I'm going to go ahead and assign an object that's going to be called Poudre. Actually, I'll call it Lincoln Q, because that gauge is at the Lincoln Bridge on your way to Odell. So we'll do read NWIS. And we could either do data or daily value. So DV, we're going to use DV. We're going to give it that site number we just pulled from the website. We're going to give it a code. So P code is what they call it. I don't know that it has to be called P code. I think it just is called code. So that is going to equal parameter code. Parameter code. So we want that to equal discharge. So if we go back up to the website, we can see that discharge is 0060. So we'll do that, 0060. And then we're going to give it a start date. Let's just say we want it to be sometime early in the it's passed. So let's say it's going to be 1950. We'll start at the water year, so 1001, and then we'll do 2019, 1001. Okay, so now I forgot to say that this is the end date. So now I think when I run this code, it should download this data pretty quickly. It's 50 years of data, so it might take a second. So that leaves us with 16,000 observations. So we can just quickly look at this object using the summary command. So we have something called agency code, so that's going to be USGS. We have a site number, which is what we fed it up here. We have the dates, so apparently the data starts only in 1975. Since I know that now, I can just kind of click up here and say 1975. And then we have this column X00600003, and that's just the USGS's way of cataloging the parameter we downloaded. So 0060 stands for discharge, and 0003 stands for how the sort of units of that discharge. I'm fairly certain this is in CFS. So why don't we go ahead and add a line here where we rename it, and we'll rename it QCFS, and that's going to equal X underscore 00060 00003. And then that code, this part right here, that's just talking about a quality code. So basically, is this data part of the record? Is it provisional data because it's live streaming from a sensor? So we're just going to say Q code, and that's going to equal X 00060 00003 code. So now when we re-download it, it's going to rename those columns, and they're just going to be a little bit more human readable. And so if we do our summary again, we get the same answer, and now we have sort of a relatively nice, clean Q data set. So one thing that you notice here is that I'm sort of rewriting quite a bit of code, and let's say now I just happen to know the code for the Environmental Learning Center discharge station. So this is about 5 miles further south. It's all the same numbers except this becomes an 8. And I can rerun that. I can go ahead and look at the data. Just make sure it's the same. The start date's a little bit later, but basically these are similar data sets. I'll re-add this because I deleted it on accident and I meant to comment it out. And so now we have 2 data sets, but what you can see right away, and we've been doing a lot of this in class, is I just repeated a bunch of code. So all this stuff is sort of identical, and there's a way to prevent, let's say I wasn't just doing 2 sites, but I was doing 5. Rather than rewriting all this code, particularly the renaming section, I can write my own function. So this is sort of the, let's say the sort of non-functional way, non-function oriented method. And then we can get the exact same data using a function oriented method. And so what we're going to do here is we're going to collapse all these commands and special things into a single function that just sort of does this automatically for us. So what we'll call it, so the way you write a function is you name it something. So we'll call this Q downloader, because we're always going to be downloading Q, which is discharge. And we're going to say this is a function. So now I'm saying, hey, I'm going to call a function. It's going to take one parameter called site number, and we'll just set that default. So when I put in equals here, I just set a default, and we're going to just set that default to be the Poudre River. And if you didn't want your users to have a default, you could leave this blank, and it would spit up an error if they didn't put in a site number, which can be useful to do if you don't want them to download stuff without having explicitly to call it. In this case, we want to sort of make sure they download as much data as possible. Let's say we're only interested in data that goes back to at least, or not to at least, but starting in 1950. We'll take any data that started after 1950. So now inside of this command, inside of this data, this function, we're going to put all this stuff we just wrote up here into this data set. So we're going to read this data. I'm going to just call it df. It's our data frame. And here, instead of this number right here, we just need to replace it with this name. So this becomes site number. And then it's going to download this parameter code, and we're forcing it to always be discharged. So now we're taking this option away from our user. I'm just going to clean up the sort of syntax of this code a little bit, so it's a little cleaner to read. We're going to force a start date. Let's go ahead and be a little more open, and we'll say a start date of 1950. And then we're going to also force an end date, which is the end of the water year this year, or the start of 2019 water year. And then the user, we're going to force it so that if the discharge comes down having this parameter code, x00600003, we're going to just rename it for them, and it's going to be called QCFS, and then Q code. Okay, so now we close the curly bracket. So these curly brackets right here and at the end, oh, there's already one. Those curly brackets basically say open up the function call. So we're defining all the things the function will do inside those curly brackets. And then when we exit the function, we want to make sure it's very clear what we're returning. So here we're just returning this data frame we made, which we called df. So now using this QDownloader function I wrote, so I need to run this so that it saves the function. Oops, something was wrong. Let's see. Okay, I think I just had an open parentheses. So that function works. And then now we have this function, and instead, all we have to do is feed this function a single parameter name. So now we can bop around the US and download different data sets. So we'll say Lincoln Q. So we're going to remake the same data set we made up here, but it's going to be a much cleaner call because we're just going to say QDownloader. So this is a function we made. And all it takes is a site number. So now we just make a site number, and we're going to explicitly call it here. And now that function will go to the internet, grab it, and rename the data. And so we can do summary Lincoln Q. And now we have this sort of full data set. And we'll do ELCQ as well. 52280. So these are two sites that are really close to each other, and maybe once we've downloaded them, we actually want to stack them on top of each other so we can plot them sort of easily in maybe like a ggplot call. So to do that, up here, what I'd have to do is I would have to say mutate site equals Lincoln. And then I could rerun it, and then down here I would say mutate. So now I'm just adding a column that tracks where the site comes from. And I'm going to call this ELC. And then I would say combo data. And then I would bind the rows of Lincoln Q and ELC Q. And so now I have a data set that, if I do a summary on it, is going to, it's going to have a new column called site, and that's just going to keep it organized so we know which data set's coming from Lincoln and which one's coming from the ELC. The nice thing about sort of doing this function is we could add an option inside our function, and we could call it site, and we could say equals. In the case of the sort of default, it's going to be Lincoln. And then we can add this mutate call, and it's going to equal site. Let's call this site ID so that we don't get it confused with the name of the new column. We'll do site ID. So now we added the ability to add site directly into the function call, so we don't have to write out the mutate command over and over. And we can do Lincoln. And now we rerun it, and it's just going to append that new column. And down here, we can do the same thing. And then we can make the same combo data set, bind the rows, and ELCQ. And if we look at this data, then we have the same identical data. And the nice thing here is this is just less verbose. It's a little cleaner to read. And the definition of how we made the function is all up here. So if you really wanted to go in and change anything, you can just go change the function and rerun it over and over. And so this sort of like just makes working with larger data sets or doing repeated tasks a lot easier and cleaner to read. So it's a nice way to do that. And now maybe let's go ahead and plot this data. So we'll say plot discharge data. So we're going to work with ggplot here. We're going to plot this in a few ways. First, we'll do the time series. X-axis equals date. So let's go ahead and we're going to call ggplot. We're calling it on the combo data. The aesthetics, the X is going to be date. The Y is going to be QCFS. And the color is going to be site. And then maybe let's do a geom line here because these should be tracking as lines. And I'm going to just run that. And you'll notice it'll take a while to run. Oh, I made a mistake. So I quoted this site here, and you'll see in the bottom right, it actually just thinks that I mean they all should be called site. Really, I meant to call the column name. And that should just be the word site unquoted. And so now you get the ELC in Lincoln, and we can do all of our aesthetics things to make this prettier. We won't do that right now. From this graph, the way it is, it's actually really hard to see because there's so much data that it's hard to see sort of any differences between the sites. So maybe a different way to sort of look at this data is a histogram. Sorry, a density plot, which we've already made as a homework assignment, but now we can do ggplot combo data aesthetics X equals date, Y equals QCFS, color equals site. Oh, X is not going to equal date, I lied. We just want to look at the sort of distribution. Are these distributions shaped differently? And so all we need is an X, and then we'll do geom density, and that's going to plot the sort of probability density function between these two sites. And right away I can see that because Q is a very sort of logarithmic, has logarithmic behavior, so we probably want to get it on a log scale. So I'll just put the x-axis on the log scale, and then we can see how these distributions look different. And basically what you can see is that there is a real difference in distribution, and the Lincoln Bridge tends to have some longer times at higher flows. And if you know the Poudre River, you know that this reason is there's a bunch of canals between the Lincoln site and the ELC site. So normally when you go downriver, you should have higher flows, but in the western United States, we often have canals taking those flows out of the river. And that's why you have higher flow further upstream at the Lincoln Bridge more frequently. So that's kind of an interesting thing. And the other thing that you notice is that these are what's called a bimodal distribution. So you can sort of like explore your data in this way, where you have two peaks. You have one at maybe 8 CFS and one closer to 100. But still, I don't love the way these are plotting. I think it's hard to see, particularly if we go back to the time series. You're not really getting an intuition about what's going on in the system, especially over time. So this is where this other other program comes into effect called dygraph. So we'll make an interactive version of this. And to learn how to use dygraphs, you can use $dygraph, but I always just go back to dygraph RStudio because they have a little online helper and it's a lot easier to actually see. So dygraphs is really nice because these are time series data sets, but they zoom and they're just a little bit easier to read. And you'll notice up here a sort of major difference between dygraphs and ggplot is that this is a wide data set. So cbind means column bind, and it's column binding these vectors called mdeths and fdeths. I don't actually know what that did. Lung deaths apparently, and male death, female death probably. And basically it's going to take each of those wide vectors. So we have fdeths and mdeths, and it's going to plot them out. But that's a wide data set, not a long one. They're not on top of each other. They're right next to each other. And so if we go back to our data set and sort of just take a look at the structure of it, you know that there's only one column of CFS, and to make it work with dy graphs, we need two. So why do you do this? Structure. So from previously in class, you should know the way that we're going to change data is we're going to use the command spread, which is now one of the libraries I forgot. So we're going to load the library tidyr. And we're going to say spread on combo data. And the key is the site number. Actually, it's actually the site name. And to make this cleaner, I'm actually going to remove some columns that we don't need. So before I spread, I'm actually going to do a select to remove columns I don't want. So I'm going to do combo data. I'm going to select out agency code. So the minus just selects out that data. I'm going to also select out site number because we've replaced that essentially with site name. And for our purposes today, we're not going to focus on the quality code, although if you were doing this kind of analysis for your work, you would want to make sure you're using high quality data. So I'm just going to remove that as well. And now I can spread this, and the key equals site, and the value equals QCFS. And let's see if that works. It might not. So now we can look at the structure of wide data. And what we have is exactly what we want. We have a column that has the date and a column that has the ELC queue. And you'll notice it starts with an A's, which we know because it didn't start till 1979, and a column that has the Lincoln queue, so the Lincoln discharge. And now we can sort of use this in dy graphs, but first we have to make what's called a time series object. So we're going to make an XTS object. So we'll say wide XTS, and we'll call this function called XTS. And what XTS wants is it wants the columns that you want to plot. So we'll do ELC and Lincoln. And then it wants to know how is it going to order those by. And in this case, it's going to be wide data date. So it's just a column called date. So now we've made this XTS thing, which apparently is another library I didn't load. Time series objects. Time series plotting. So now we've widened this data into the proper form. What? Oh, I didn't load it. Library XTS. So now I've loaded it, and this should work. And the great thing about dy graphs is once that thing is a time series object, so we can look at the structure of that. It knows that it's a time series object, an XTS object. And when it knows it's an XTS object, dy graphs, the command, knows exactly what to do with these kinds of objects. It's going to make an interactive time series object that is easy to zoom around in. So we're going to do dy graph wide XTS. And now we have almost 40 years of daily discharge data, and we can zoom in on it and look at differences in the sites. So in May of 1983, despite being lower in the river and therefore having higher or a larger catchment area, the ELC was lower discharge. So when I see that, I'm thinking, okay, a canal was on. Maybe we can zoom in to these really big peaks. I'm guessing this is the 2013 flood. So this is this massive flood. One thing you'll notice is the discharge data looks wonky. Some of that could be because discharge is extremely hard to measure at really high floods. And the other thing is this is the sort of record flood that they have in the database at 7,500 CFS, which is sort of a major flood. And then we see that the next year we actually had a pretty high snowmelt flood as well. So this is sort of a lot easier in my mind to explore actual time series data. We can see that in general all these sites sort of move along with each other, and that's pretty sweet. So now we made this interactive graphs, but let's say we wanted to keep doing this kind of approach over and over. I would suggest when you're doing this kind of like data manipulation that is repetitive, this is another case where we can make a function. So I accidentally deleted this. This is one way to make the interactive graph. Another way is to make a function that does this. So we can benefit from the code we wrote up here by just grabbing it. First I want to make a function. I'm going to call this the XTS prep. So this is just like, we're going to make this into an XTS object inside this function. And the function is just going to take a data frame, which we'll just call df. And now is where I want to paste all that stuff I just copied. Except here, instead of calling it combo data, which is the specific data set we've been working with, I'm going to call it df. And that's what the function will know to look for. And I'm going to properly indent stuff. You'll also know in one case down here, I properly spaced my equals. Up here, I didn't. In general, you should have a space between equals. I don't always do that, but it's a good thing to try. And then in here now, we've made two objects. And this is where it gets really important that you use the return call, because what we want to come out of this is the XTS object. We don't want this wide data object. So we're going to do return wide XTS, and then we're going to run this function call. And now, when we can make the same wide XTS object, but we can make it inside of this XTS maker, and all it will take is our combo data. So now we can just test that that's the same graph as upstream. So we'll do dy graph at wide XTS. And indeed, we have the same graph. But the nice thing is now we have a function that can make this graph. We can make it for different data sets. So let's try and do wide ELC, XTS maker, and then here I'm just going to use ELCQ. This is the most cryptic thing, and it always happens. So I'm going to rerun the function call. I'm going to rerun wide ELC, and then we're going to get this error called object link and not found, and that's because I did poor function writing. Up here, I called a specific column I wanted. But of course, if we were using different sites, maybe you're working on the Big Thompson or some other place, you're going to have different site names. And this was sort of bad practice. I shouldn't call the column names I explicitly want in this particular case. What I should be doing is saying I do not want the date column, because the way the XTS object works is it plots whatever you put here against whatever you say you're ordering by. And so if I kept the date, I would have a plot that would be date against date, which we don't need. We just need date against something else. So all I'm doing with the select call here is removing the date. So now I'm going to rerun this XTS maker and rerun the wide XTS just to make sure. We can check the wide XTS produces the same graph with this new call. Indeed it does. Looks really kind of nice and super zoomable. And then we can rerun it just for the ELC if we want. It's kind of pointless in this particular case because we already have ELC plotted in the other one. But if you just wanted to see a clean graph of just the ELC data, then we would do dy graph wide ELC. And now we have just the ELC data. So in class, we're going to go over writing some more advanced functions, and hope this helps.